Good morning, everyone. Welcome to VR with Metal 2. My name is Rav Jaraj, and I'm a member of the GPU software team at Apple. So as you saw in our Introducing Metal 2 session, we've enabled some great new features this year. And in this session, I'll be focusing specifically on the support for VR that we're adding with Metal 2. So I'll start with a brief summary of what we've enabled in macOS High Sierra, and then take a deep dive into what's required to build a VR app, and then end by providing some details on how you can take advantage of the new external GPU support that we've added to the OS. All right, I hope everyone here knows what virtual reality is. But just in case, it's an immersive 360-degree 3D experience with direct object manipulation using controllers and an interactive, room-sized environment that you can explore thanks to highly accurate motion tracking. Now, we at Apple think that this is a great new medium for developers like you to create new experiences for our users. And Metal 2 enables this support in 3 ways. First, by providing a fast path to present a frame directly to the VR headset with our new direct-to-display capability. Second, by enabling new features like viewport array that are specifically targeting VR. And finally, by providing that foundational support for external GPUs so that developers have a broader range of Mac hardware, of VR-capable Mac hardware to work on. So let's get right into what we've enabled with macOS High Sierra. So we've added built-in plug-and-play support for the HTC Vive VR headset. And this headset works in conjunction with Valve's SteamVR runtime, which provides a number of services, including the VR compositor. Valve is also bringing their OpenVR APIs to macOS so that you guys can create VR apps that work with SteamVR. We've been working really closely with Valve over the last year to align our releases, and both SteamVR and OpenVR are available to download in beta form this week. So before I go on, I'd like to describe what the VR compositor actually does. So in a nutshell, it distorts the image that your app renders to account for the lens optics in the VR headset. In this example, you can see the barrel distortion that the compositor is applying to account for the pincushion effect of the lenses. Now, in practice, there's actually a lot more complexity under the covers, and the compositor has to handle things like chromatic aberration and also presenting a chaperone UI so that developers know the bounds of their VR space. All right, now that you have built-in support for a VR headset, a VR compositor with SteamVR, and an API to write to, let's dive right into how you build a VR app. Well, you have 2 options. Your first is to use an existing game engine that has VR support. And this is a great option that many developers prefer because it hides some of the complexities of the VR compositor. It also provides a familiar content creation toolchain. Now, your second option is to write a native VR app that calls OpenVR directly. This gives your app full control of rendering and synchronization with the VR compositor, but at the cost of some additional complexity. Which path you take depends on the goals of your app. But let's start by talking a bit about the game engines. So you saw Epic's Unreal Engine 4 in action in the keynote, and it's a powerful platform on which to build your VR experiences. VR support will be coming later this year, and you can find tutorials and other information on Epic's website. We're also really excited that Unity is bringing VR support to macOS in a future release of their engine. We've been working closely with them to ensure that the engine is optimized for both VR playback and development using Metal. So I'd like to take a moment at this point to talk about a specific Unity title called Space Pirate Trainer. So we've been collaborating with Unity and iLlusions to bring an early preview of Space Pirate Trainer to macOS. And the speed at which iLlusion was able to bring their app to our platform was truly astounding. They had a working build in just a few hours, and then a stable, fully playable game in just a handful of days. We've been having tremendous fun playing with this game and think that it's a great representation of the type of VR experience that you can build with Unity. We hope you get a chance to check it out at WWDC. We think you'll love it as well. So Unity and Unreal Engine 4 are two great options for VR development. But you can, of course, choose to write a native SteamVR app that calls the OpenVR framework directly. Now, we'll have details on how you can add the framework to your app later in the session, but you can download binaries and API documentation at the OpenVR GitHub. There'll also be a Metal-specific sample app available to download in the near future. But to give you a taste of what's involved, I'd like to now provide a primer on VR app development in a segment that I like to call VR App Building 101. So we're going to cover a few things here. We'll start with an overview of some of the challenges involved in VR development, and then talk a bit about some unique considerations on our platform, and then take a deep dive into the anatomy of a VR frame, and then end with some best practices specific to VR apps. So we've got a lot to cover here, so let's get started with the overview. So a traditional non-VR workload targeting a 60 Hz display has around 16.7 milliseconds to do work for the frame. And in many cases, the app has the entire frame budget to do work on the GPU. A VR workload, on the other hand, has to target a 90 frame per second display, and it needs to hit this target to achieve a smooth, judder-free experience on a headset like the Vive. So this reduces the available frame budget to around 11 milliseconds. Additionally, the VR compositor has to do work on the GPU to prepare the frame for the VR headset. This can take up to 1 millisecond, leaving your app an effective frame time budget of around 10 milliseconds, which is about 60% of the non-VR case. And if that wasn't enough, your app also has to do more work every frame. This includes stereo rendering for the left and right eye, and also rendering to a higher resolution in many cases. The Vive headset has a resolution of 2160 by 1200. That's 25% more pixels than a 1080 display. Additionally, many VR apps render at a 1.2 to 1.4x scale factor to further improve quality. So in summary, your app has a lot more work to do in less time. Welcome to VR development. All right, let's talk about some platform specifics. So Metal 2 introduces a new direct-to-display capability for supported headsets like the Vive. This is a low-latency path that bypasses the OS window compositor and gives the VR compositor, like SteamVR, the direct ability to present a surface onto the VR headset. This avoids any pixel processing or additional copies by the OS. Now, it's worth noting that in order to guarantee this fast path, the macOS does not treat VR headsets as displays. They're hidden from the system and offer no extended desktop capabilities. So to summarize, we move from a model where you can present, or an app presents to a display through the OS window compositor, to one where a VR app can present to a headset directly through the VR compositor. And that's our direct-to-display capability for VR with Metal 2. All right, keeping with the theme of macOS platform specifics, let's talk a bit about how your app selects a Metal device to use. So on macOS, the VR compositor can query the OS to find the Metal device for the GPU that the headset is attached to. And for performance reasons, your app will want to select the same device that the compositor is using. So we've worked with Valve to make sure that there's an API to do this. Simply call getOutputDevice to get the Metal device that you should render to. It's that simple. Now let's talk about managing drawable surfaces on macOS. So the VR compositor and your app each maintain separate pools of drawable surfaces. And in a typical frame, your app will render to textures that it owns, submit these to the VR compositor. These will get composited onto a surface that the compositor owns, and that's the surface that'll get presented to the headset. And on macOS, iOS surfaces are ideal for transferring this rendered data from your app to the compositor. So make sure that you create metal textures that are backed by iOS surfaces. As a refresher, let's take a quick look at how you create those textures. So you'll want to build a texture descriptor that specifies the render target usage flag, since your app will be rendering into it, but also the shader read usage flag, since the compositor will be sourcing it as an input. And then, to create your left and right eye textures, you simply pass the iOS surfaces that you previously allocated and this texture descriptor to new texture with descriptor. All right, I'd like to now take a few minutes to talk or to describe a typical frame in a VR app. This is important because your app and the VR compositor need to work in lockstep. As I noted before, the rendered output of your app will be passed to the VR compositor for additional processing on the GPU. And since the GPU is a shared resource, synchronization and when work is scheduled matters. So let's start at the beginning of the frame. Your app will need to query the VR system to get the headset poses that it needs to render the frame. For SteamVR, this is done via the waitGetPoses call. And then your app can encode the render commands for that frame immediately after getting those inputs. And then once you've encoded your command buffer, you can commit it to metal to queue onto the GPU, and then submit your left and right eye textures to SteamVR. This will wake the compositor so it can start encoding its GPU work for the frame. And then since ordered execution matters, your app will also need to signal the VR compositor when work that it sent to the GPU has been scheduled. So for a metal SteamVR app, you simply wait until your command buffer has been scheduled, and then you can call the SteamVR post-present handoff function. This will signal the VR compositor that it can commit its work to the GPU, and it'll get queued up in the right order. So let's see what that would look like in your draw loop. So at the top of your loop, you'd have your waitGetPoses call to gather the inputs from the headset. You'd then build your command buffer to render your scene and commit it to the GPU. And then at this point, you'll submit your left and right eye textures to SteamVR. And then once you've waited for that command buffer to be scheduled, you can call post-present handoff to tell the VR compositor that it's now free to commit work to the GPU as well. So one more note before I move on. It's worth noting that as we extend this diagram to include the next frame, it's waitGetPoses and not the vertical blank that defines the start of the frame for your app. This is an important thing to keep in mind, and we'll be coming back to this very shortly. All right, let's move on to talk about some best practices. So the first is to avoid introducing a GPU bubble at the start of your frame while encoding commands on the CPU. So helpfully, SteamVR offers a useful mechanism to let you start work for that frame early by giving your app a 2 to 3 millisecond running start. So this should look very familiar. By aligning the start of your frame with waitGetPoses, you'll ensure that you're taking advantage of this optimization and getting that running start. All right, next, make sure that your app is not building large monolithic command buffers before committing them to the GPU, as this can also introduce GPU bubbles. Instead, you want to split your command buffers where possible and commit them as you go to maximize GPU utilization in the frame. So the next optimization that we recommend is to try and coalesce your left and right eye draws together. the Metal 2 viewport array feature provides a great mechanism for you to do this by letting your app select a per primitive destination viewport in the vertex shader. This can substantially reduce your draw call overhead, as you can now render to both the left and the right eye with a single draw call. So let's take a look at an example of how you can adopt viewport array for your Metal app using instancing. So the first thing I want to point out is that you'll need to create a texture that's twice as wide, because you'll now be rendering both the left and right eye scene to the same texture. And then you simply create your viewport array that defines the bounds for your left and your right eye viewports. And then you can pass this viewport array to your render command encoder using the new set viewports API. And then at this point, you'll want to make an instanced draw primitives call with an instance count of 2 to issue the draw to your left and right viewports. We'll be using the instance ID as our eye index in the vertex shader. So let's take a look at that vertex shader. So the first thing I want to point out is that the viewport is selected via the new viewport array index attribute. And then, as I previously noted, we're using the instance ID as our eye index, and we'll be able to use it to access our viewport-dependent data, like this model view projection matrix in this example. And then finally, you do want to associate your viewport index with the instance ID so that the right viewport is selected when rasterizing your image. And that's how you use the new viewport array feature to reduce the draw call cost in your VR apps. All right. The final optimization that I want to talk about today is really a general best practice. You want to try and reduce the number of pixels that you're shading every frame. So due to the nature of the lens warp, about 15% of your rendered scene is not actually visible on the VR headset. This is represented by the blue regions in this image. Luckily, SteamVR offers a mesh-based stencil mask that is specific to the Vive headset that you can use to cull these pixels. It's really easy to use and provides a substantial benefit. All right, that brings us to the end of our brief journey into building a VR app. So with that background covered, I'd like to now introduce Nat Brown from Valve Software to come on stage and talk a bit more about SteamVR on macOS. Thanks, Nat.
Thanks, Rob. Hi, everybody. I'm Nat. I work on VR at Valve. So if you don't know Valve, we're a game company. We distribute games, and we have a community of gamers that play on Steam. It turns out games are actually a super interesting crucible for user interface and human-computer interaction. And at Valve, we do a lot of experiments around games and input. So years of VR prototypes really didn't click for us for making games or any other kind of content until we found this sweet combination of 90 hertz, low persistence displays, accurate room scale tracking with 2-track controllers. We consider this a magical threshold for VR. I like to think of it as kind of similar to how when you first used a smartphone with low latency, accurate touch, it really felt magical. That's what this magical threshold is for VR. Once room scale VR really clicked for us, we knew that we could build VR games and VR content. We license aspects of our VR technology, like base stations, headset, lens designs, and so forth, non-exclusively to partners like HTC and LG. And we have a big program that licenses lighthouse tracking technology to lots of different partners. Our approach to the software stack you've heard a little bit about already is called the SteamVR runtime. SteamVR has an application model up above and a hardware and driver model down below. Our goal here is to promote experiments in VR because we're really in the early days of what VR is and what the content's going to be like. We wanted to make this model so that people could experiment in VR hardware and content and reduce risk. So you can go out, maybe not you, but somebody can go out and design a new headset or a new tracking system or new controllers. And then you can come to an OpenVR platform and you can write a driver that plugs right in, and you'll have access to all the existing content that's already running. That'll give you real-world tests that make your hardware better, because you and your customers can compare your new idea directly with other hardware that's already out there. So hardware developers don't have to develop custom content, and content developers don't have to bet on which hardware will win. They can just focus on making great content. So applications link to the OpenVR framework. It's a really tiny library, and all it knows how to do is define the runtime that's currently installed. So it finds this VR client library. That's a shared library, and that either connects to or launches the other runtime processes of SteamVR. The VR monitor process, you're going to see a lot of that little window. It's a UI and a settings application. It shows you the state of any attached headsets and controllers and the tracking sensors. The VR server is in charge of keeping track of drivers, loading alternate drivers, and it puts poses and other information into shared memory so that your application and the rest of the SteamVR runtime have access to it. The VR compositor you just heard a little bit about, this process is sort of like the Windows server. It draws scenes and overlays to the headset, and it corrects images for lens distortion, color, and one of the things that's sort of under the hood that you may not understand is it corrects for smearing and ghosting under motion. And and it also fades into a stable tracking area when applications fail to meet frame rate, because we don't want people to fall over or bump into something. So the VR compositor communicates with Metal, like you heard. It presents directly to the headset through the direct-to-display Metal 2 APIs. Let's see, last but not least, the mighty VR dashboard. That is a piece of UI that lets you select applications. It lets you control volume, other system settings. We provide a default one that shows you your Steam library and lets you choose applications, but there's actually an API, so you can write your own dashboard application as well. So Valve and Apple, we started working together more closely about a year ago. And our port to Metal from OpenGL, it didn't cost us very much. Metal's a really cool API. And it was critical for us to get VR up and performant. Our biggest request to Apple a year ago was for this direct-to-display feature, because it's critical to ensure that the VR compositor has the fastest, time-predictable path to the headset display panels. We also really needed super accurate, low variance VBL, vertical blank, events, so that we could set the cadence of the VR frame presentation timing, and we could predict those poses accurately. Predicting the pose accurately is actually more important than the time between motion happens and when the display happens. If we know when it's going to be, that's actually more important. Finally, we hit some speed bumps around inter-process and inter-thread synchronization. Once everything else was working really well, Metal was blazing fast, we had really tight VBL, but we still were having some synchronization problems. But Apple helped us find better ways to signal and synchronize with low scheduling variance between all the processes and threads involved. Okay. So my diagram of a VR frame is a little more complicated. Most of you are never going to look under the hood this far, but I thought I'd show it to you anyway. So the low persistence OLED of the HTC Vive uses global illumination. All of the pixels of the display flash for a tiny period all at once. And this is common in VR because heads move really quickly. And we want to make sure that the image doesn't smear or tear in front of the user. So the panel illuminates for about 2 milliseconds, one frame after it is presented by the GPU, because the panel takes time to charge before it can do that global illumination pulse. So over here, that's the photons coming out. We're going to follow this red frame through this sequence. So way out here is the photons coming out. Because of this timing, applications typically pick up a pose, like you heard before, from IVR compositor wait-get poses. So wait-get poses stalls and returns with a pose for that future firing of photons. So the rendering is happening here, and you present it there, here in the middle, but the photons don't go out there. So we've had to predict a pose 25 milliseconds, about 25 milliseconds out. So the 25 milliseconds is 2 frames plus the little tiny bit of running start. And you heard how running start's very important, because we want to give you as much of that 11 milliseconds of GPU time to get the most excellent pixels up in front of the users that you can. So one last thing that's happening here, you see this frame actually stretches back all the way to the beginning of the slide. And that's because this application, and and your game engine might be doing this under the covers, is kind of more complicated. It has some physics and input event processing that it needs to do, and that's costly work that's going to take some CPU time over here. But that code actually needs pose information also. It needs to know when the buttons were pressed and where the controllers were, and maybe it's interpolating something having to do with motion, or you're blocking something, or you're firing something. So this thread actually, it's going to wake up at around the same time, because wake up poses gives it this important kind of sync point, but it's going to be calling a different API, because it's trying to get a pose much further out. It's looking 36 milliseconds out, and so it's going to be calling the get device to absolute tracking poses. So I tell you this just so you know, OpenVR has some pretty deep APIs for you to tune your application so that you're predicting where the headset and where the controllers are going to be very accurately based on where you need them to be, where your code needs them to be. So the point of wake-up poses is it gives you a predictable point in time at running start, so you always know when those photons are going to come out. So last but not least, let's talk about what you would need to do to get up and running with SteamVR on macOS. So first of all, it's a tool in Steam. As a developer, get started by installing Steam and registering for a free account. And if you don't use Steam, you should. Next, install SteamVR itself. SteamVR is under the library menu in Tools. Search for SteamVR, right-click on it, choose the properties, choose the beta tab, and opt into the beta. For now, it's a beta. Then install it. We'll be keeping SteamVR up to date as we fix any bugs that you find. Finally, you want to download the OpenVR headers and the framework from GitHub. And I put a link right up there for you in the slides. So here's the funky part. You need to include that OpenVR bootstrapping framework inside of your application. The OpenVR framework that you link to, that conveys the version of the interfaces of the runtime you built and tested against. And that allows us to upgrade the runtime and to version forward gracefully, because we move this forward quite actively. In Xcode, instead of just adding the framework to your link phase, go into general settings and make it an embedded binary. So it will be installed into the contents frameworks portion of your application bundle. OK, finally, we really want your feedback. So we put some things right into the UI of VR Monitor. There's a pointer to the SteamVR support site and the community, hardware discussions, and you can report a bug, create a system report, and send it to us, or probably send it to me. You can reach me at natb@valvesoftware.com, but I'd rather you use the tool. And with that, thanks very much. I'm really looking forward to what you guys make with VR, and thanks to everybody at Apple for making VR shine on macOS. Thank you.
Thanks, Nat. It's been great working with Valve, and I'm still astounded by what we've been able to achieve over the last year. All right, let's move on to talk about the external GPU support that we've added with macOS High Sierra. So an external GPU is a standalone chassis with a desktop-class GPU in it that you can plug directly to your host system via Thunderbolt. And as noted previously, our primary motivation here was to enable developers like you to build great VR apps using a broader range of Mac hardware. There's a great workflow story here where you can use your MacBook Pro with an external GPU to get the rendering horsepower that you need for VR. But of course, there's also additional performance benefit to be had for other GPU-bound cases, like games and pro apps as well. And as you saw on Monday, we've been partnering with Sonnet and AMD to offer you an external graphics developer kit with an AMD Radeon RX 580 GPU in it. This kit is optimized for use with all our Thunderbolt 3 capable Macs and is available for purchase through our developer program today. All right, let's dive right into how you identify the external GPU. This device enumeration code should look very familiar to you. Copy all devices will give you all the metal devices in the system. And then you can identify the external GPU by simply looking for the removable property in the device. This is very similar to how you've previously identified the low-power devices on our platforms. Now let's talk a bit about Thunderbolt bandwidth capabilities. So Thunderbolt 3 offers twice the theoretical bandwidth of Thunderbolt 2, which is great. But you have to keep in mind that this is still a quarter the bandwidth of the PCI bus available to the internal GPUs in our platforms. So this is important. You have a choice now between using the internal GPU with a high bandwidth link or a high performance external GPU with a link at about a quarter the bandwidth. So you need to treat the link and the GPU as a pair when deciding which GPU you use. Additionally, users can now attach displays to different GPUs. And in this environment, there's a penalty to render on one GPU and then display on another, as that data needs to be transferred across the link. So where your content is displayed clearly is a huge consideration when you decide which GPU you want to use as well. So there's additional complexity here. But fortunately, there's a couple simple things that you can do to make your app a good citizen in a multi-GPU environment. So let's start with GPU selection. The best advice that we can give you is to render on the same GPU that's driving the display your app is on. I call this the golden rule of GPU selection. So let's extend this and build a decision tree. So if the content your app is rendering will be presented to a display, you want to select the GPU that's driving that display. This is our golden rule. However, if your app is doing compute or other offline rendering operations, then you need to decide if you prefer to use the low-power GPU if it's available. This can be particularly useful on our portables, where selecting this device can have a substantial battery savings. But of course, if you need the GPU horsepower for things like VR, you're going to want to select the external GPU. So let's get back to our golden rule and find out how you identify the metal device that's driving a particular display. Well, it turns out that this is really easy to do. There's an existing Core Graphics API that will give you this device. You simply have to get the ID for the display that your window is on by querying the NS screen number, and then call CG direct display copy current metal device to get the metal device that's driving that display. It's that simple. All right, now that we've established that each display can be attached to a different GPU, your app will need to handle GPU migration as your displays are moved, as your window is moved across those displays. So you can do that by registering for the new, well, it's not new, our existing notification handler called window did change screen. So let's take a look at what you do with this notification handler. So you'll want to start by finding the metal device that your app, for the display your app is now on, by calling the Core Graphics API that we previously discussed. You can early out if it's the same device that you're currently rendering to, since no GPU migration will be required. And then you'll want to perform your device migration and switch to using the new device for all your rendering. So that's how you use a display change notification to handle GPU migration. But what about the case where the external GPU is plugged in or unplugged from your system? Well, Metal 2 introduces 3 new notifications to help you with this case. These are device was added when an external GPU is plugged in, device was removed when it's unplugged, and device removal requested when the OS signals an intent to remove a GPU at some point in the future. So let's take a look at how you would register for and then respond to these notifications. So you'll want to use the new Copy All Devices with Observer API that we've introduced with Metal 2. This will let you register a handler for these new device change notifications. In this case, we're simply invoking a function called handle GPU hot plug. So let's take a look at it. It's really straightforward. All you have to do is check for and directly respond to each notification. But I want to point out a couple things here. The first is that your app should treat the device removal requested notification as a hint to start migrating off the external GPU. And second, if your app did not receive the device removal requested notification, then it should treat device was removed as an unexpected GPU removal. So an unexpected GPU removal is when your external GPU is disconnected or powered down without the OS being aware. So this is the equivalent of somebody reaching into your system and yanking out that GPU. And since the hardware is no longer there, some Metal API calls will start returning errors. So you'll want to add defensive code to your app to protect against this, so it can survive until it receives a migration notification and it can gracefully switch to another GPU in the system. It's also worth pointing out that if you had any transient data on the external GPU's local memory, your app may need to regenerate this as it's no longer there. All right, now on to some best practices. So we recommend that you don't immediately release devices after you migrate, as users tend to move windows back and forth across displays. Instead, employ a lazy teardown policy with some reasonable timeout. Additionally, if your app has a complex UI with a number of windows, you may need to handle GPU migration separately for each window. And then finally, we recommend that you profile your app in multi-GPU situations to ensure that you're not needlessly transferring data back and forth across the GPUs. All right, let's tie it back to VR with some best practices specific to this use case. First, and most obvious, make sure you attach the VR headset directly to the external GPU. Less obvious, but equally important, you want to make sure that your app is presenting its UI or the mirrored VR content to a display that's also being driven by the external GPU. This will ensure that both the VR compositor and your app are rendering with the external GPU. And finally, make sure you cache as many resources as possible on the external GPU's local memory so that you're not streaming data across the Thunderbolt link unless absolutely required. All right, so this brings us to the end of our session. So let's quickly review what we've covered today. So the big news is that you can now develop VR content on macOS. We've added built-in support for the HTC Vive headset, and we've partnered with Valve to enable an optimized version, an optimized metal version of the SteamVR runtime on our platform. Additionally, two of the most popular game engines, Unity and Unreal Engine 4, will be bringing VR support to the Mac in the near future. But of course, we also encourage you to build your own native VR app. And finally, we've added support for external GPUs. And we hope that this motivates you to ensure that your app is a good citizen in a multi-GPU environment so that you can take advantage of that additional GPU horsepower. We're really excited to see what you guys are going to be able to build with this new technology. So be sure to check out the other sessions on the Metal track. We had a great Introducing Metal 2 session yesterday. If you didn't get a chance to see it, I encourage you to watch the video online. We have 2 additional sessions in the afternoon tomorrow, Metal 2 optimization and debugging, and using Metal 2 for compute. We hope to see you there. I'll see you there. Thank you very much, and have a great WWDC.